Next up, I'm thrilled to introduce Oleksandr Paraska. Oleksandr has worked as a software and data architect for more than 15 years. He is currently CTO at Togal.ai, a startup bringing AI to the construction industry. Oleksandr started his current role as a consulting engagement through Togal.ai, a network of top global technical talent that's changing how companies do machine learning, where he now heads up network admissions. Through his career, Oleksandr brings deep experience working on ML systems and leading teams. At AdBlock Plus, he built and led a team of engineers and researchers to deploy ML to millions of devices. At CAPTCHA, he built a highly scalable system for bot classification running over 100,000 requests per second with real-time insights into model performance and data drift. Oleksandr, over to you.
Hi. This is a talk about AI meets real world, how we deployed an AI solution in construction industry. First, a few words about me. My name is Oleksandr Paraska. I am the Chief Technical Officer of Togal.ai, and also I'm a Head of Admissions at Togal.ai. Togal.ai is a construction tech startup who are building a solution for pre-construction space, and I will talk about that later. And Togal.ai is a company, is a community of machine learning experts who are available for contractual work for part-time or full-time, depending on your requirements. So first, before we begin, maybe a quick agenda so that you have an understanding what to expect from this. I would like to set up the scene, present to you the challenge that we had in the construction industry, and then describe a bit how we built organization to solve the challenge. I will go a little bit deeper into technical things that we have built and maybe describe some of the machine learning models that we had to train. And then I will finish off with the lessons that we learned from all of this experience, and hopefully they will be transferable to other industries that are of interest to you. So the challenge was basically started in a very different way how typically startups start, at least from my experience. So typically startups start from the statement that, hey, we have this cool algorithm or cool technology, where can we use it? This was completely opposite. It started in a construction company, a general contractor company, biggest in Florida, coastal construction. And they looked at their typical construction process and tried to identify all of the places where they can optimize their construction, their processes. And so they identified a few places where they could benefit from some innovation, and then they try to kind of understand how much would it cost if they optimized each of those. And only from there, they try to go and look for possible solutions and build organization to maybe fix or solve all those solutions. And then, of course, they try to execute, and we can talk about that next. So really quickly, typically how the construction looks like. This is a project lifecycle in construction. You can see there's a pre-project where people trying to understand what is it that you want to build. Then there's pre-construction, then when they're designing and understanding how much will it cost, and then there's actual construction. And there's, of course, post-construction when you need to maintain the building. In this project, it was identified that there is a lot of inefficiencies in pre-construction phase, which is in between design and bidding. And typically what happens currently, at least in the United States, is that after architects have designed the buildings, typically what happens, you need to understand, well, how much would it cost for you to build this, such a thing? And then almost always everyone sends everyone else a PDF of a plan. And so that means that the architect, they deliver a plan to a general contractor then sends it out to multiple subcontractors, and then everybody has to understand, well, how much would my part cost, how much would my part cost, and then general contractor will just add it all up. So that's a brief introduction to construction, but in general, it looks something like this. You'll receive a floor plan, which is a floor plan of a hotel here, one of the floors of a hotel. And you need to understand, well, how much will it cost for you to build your part? Let's say if you're a flooring contractor, you need to understand, well, what's the area of that floor that you need to build. Or if you're a drywall contractor, you need to understand, well, how much linear feet is there, and so on and so forth. So typically, like I said, what happens right now in the industry that people are sending a PDF one to one another, and then they need to make some estimate how much square footage or linear footage is there in each floor plan. And that happens multiple times a day, and that doesn't only happen on the project that you have won. You also need to bid on the project, so you are doing many more bids than actual work. And I will show you in a few seconds how it looks like in the real world right now, and that's not great. So typically, what happens now is people, let's just call it before Togal, people literally have this software which is built somewhere in early 2000s, and they go and literally trace each polygon. They try to be as precise as possible. And then, it will take you quite a lot of time to go and trace all of the buildings. Sometimes it's 3 hours, sometimes it's 1 day. But this is a Togal solution that we built. So instead of you doing the tracing, you just go and hit this Togal button, and then automatically in a few seconds, it extracts you all of the meaningful information. And all of the information that we extract, we'll talk about it later, but this is generally the gist of it. So instead of you doing coloring of the floor plan, you're focused on the high value tasks. Well, how do you optimize something? How do you increase the efficiency, and so on and so forth? So that's the premise of the product. And we'll move on. How did we approach this problem to begin with? So this is a wording map that we built. So just to understand what are the kinds of things, what are the risks that we have to do, and kind of what are the assumptions that we are making. So we understood that we need to build some sort of a automated takeoff software as a service solution. We understood that this has to be web-based because otherwise it would not make sense to build it this day and age. So that solution would definitely have a website, which is well, variable to the right here. So as you can see, that's the website. And if you're not familiar with Wordly maps, it's a map where on the left you can see solutions that are very custom made. So you need to do a lot of work, a lot of thinking. It's very unique, bespoke to you. And on the right, everything is like a commodity. It's not anything that is super unique to you. So we understood that it's just a marketing website. For marketing website, we don't need to do any custom development. You can just use some no-code tool and be done with the website, call it a day. But on the other hand, we understood that we will have to build a lot of custom code for the application that would have to be delivering our machine learning. So we understood that there has to be some sort of front end and back end and some infrastructure. We have already assessed that infrastructure is probably already a commodity with all of the cloud providers. So it's not a big worry. So we need to focus on the things that are very custom built for us, because that's our unique value proposition. This is what we thought in the beginning of the product or of the project. And if you can notice here, there are two things that we have made an assumption, which I think were incorrect. First, we thought that machine learning is kind of like a product already. So if you just feed it the right database or data set, then it will be almost like an automated way for us to find a proper model. You can use neural logic architecture search or AutoML, and that will be just a way for us to train our machine learning models. So we thought that's pretty commoditized at that point. And the project started 2 years ago, so that was number one assumption that we made. And we also thought that annotation should be, pretty straightforward at this day and age, because there are many annotation companies out there, and you can just, if you cannot do it on your own, you better just move it into this annotation company. On the other hand, we made an assumption that we do need some machine learning talent, which is a requirement, of course, for the startup like this. And we thought that has to be very unique. We have to hire the talent in-house so that we will be very unique in that sense. So these are the assumptions that I think that were proven wrong, and I will just talk about really quickly about that. So on the right here, I will show what actually happened in the real world 2 years in. So starting from annotation, it has proven to be much harder than we thought to annotate a construction floor plan because it actually requires a lot of knowledge about construction. You have to be an architect or almost an architect to be able to properly annotate a floor plan. So that meant that we had to go from like this custom, ready-made, available solution for annotation to something custom-made that we had to bring in-house. So that was learning number one that we had to change on the fly. Same for annotation tool. We decided that we actually are better off if we are building our own annotation tool because it's very similar to what we are providing to the architect. So that only makes sense. But it wasn't dictated by any other requirements, only just a requirement of reining in complexity. On the other hand, which I think is an interesting factor, we learned that we don't actually have to have, at least in the beginning, a machine learning talent as a hired for the company. We learned that there is a possibility to just hire different kinds of people and see if they work and see if they can deliver value. In our experience, that worked much better than if we had hired a machine learning talent in-house in the beginning, because you never know what kind of expertise do you need unless you're further along in the product. So in the beginning, we just thought we knew how to approach this project, but it was very uncertain. Do we need a computer vision person? Do we need somebody who's experienced in segmentation models, or maybe object detection, or both? Or maybe do we need a data engineer? All of those were floating, and so we had no idea how to approach it. And that's why like this me wearing two hats comes into play, because we were able to try out different profiles of people using the Togal.ai model. And then once we settled with enough people and we understood that this is the way to go, we were able to bring them back into custom built into this in-house company way. So I think that was maybe the most important learning, that you don't have to start with a custom talent. Actually, in most cases, for most startups, you just need someone to tell you what is the right way to do, and then you can start into it. But otherwise, all the rest things were pretty much spot on in this learning. So really quickly, I want to talk about what is it that we have actually built. We have actually built a lot of machine learning models. So to begin with, as you can imagine, to be able to read the floor plan, you need to discern which pixels are walls, which pixels are not walls. And that is it seems easy compared to understanding ImageNet and understanding what is a cat, what is not a cat. But actually, if you look at this floor plan, it's pretty complicated task. So even for me as a human, I would not be able to know which parts of the floor plan are walls, which are not walls. So you can see on the left here the input, the floor plan, and on the right, this is the output of our machine learning model. Definitely, it's not perfect in this scenario. We have much improved since then, but I just wanted to show you like, how did it all start. So you can see it's taken into account most of the walls, but also it picks up the legend and some other bits that are not necessarily required here. So this segmentation model had its own problems when deploying, and I will talk about the problems in the real world in a few steps, but that's essentially what the first model does. But if you think about what should happen next, once you have the segmentation model, really you're not interested in pixels, you're interested, of course, in vectorized data. You need to know, well, how long is this line and where is the room here, and so on and so forth. So one of the other learnings for us here was that machine learning part is actually the easy part. Then to go from the segmentation mask to the actual vectorized, semantically meaningful data is the even harder task. And if you measure it in compute milliseconds, the vectorization part is 10 times, even sometimes 100 times longer for us than the pure machine learning part, because it's so commoditized and it's fairly straightforward off-the-shelf mask. But one other thing that we discovered, and that's why I mentioned that we thought originally that machine learning will be at least the product, and then in the end it turns out that we needed to go and do some much more custom development. And the reason behind that is that there were different teams experimenting with this, and the first team, of course, tried to do an AutoML approach to this problem. So they have a segmentation problem, and they try to produce a segmentation model that is finding the best kind of, the optimal model. That, of course, turned out to be a very suboptimal solution because they went into all sorts of different problems, and then the AutoML, as you might know, or neural architecture search requires a lot of compute, and so they did a lot of compute, spent a lot of money on compute, and then still were not performing very well. And then they just the moment when I personally was brought into the project, they were stuck on just trying to deploy their AutoML solution to TPUs, which I'm not sure how it's now, but back in the day it was not very not great to support for TPUs for AutoML. So we had this problem, and initially our first task was, well, how do you solve this problem so that we can just train AutoML solution on a TPU? Instead of solving this problem, of course, a better solution was to just take a step back and go and think, well, what is the best model? And rely on your machine learning talent and rely on the computer vision expertise that people in the team have, so that instead of relying on algorithm to find the best model, we found a much better model on our own using the priors that we were able to put into the models. So that's the learning number one. So machine learning, even though there's lots of tooling out there, lots of no-code solutions, low-code solutions, it's still not really possible, at least in this case, to build a solution without deep expertise in computer vision and machine learning. Of course, other than just the segmentation model, we also needed to provide other sorts of extracted information from the floor plan. So in this case, we also have built an object detection model, which in the beginning was YOLO 5, then we have upgraded to a much better model. So you can see it's pretty off-the-shelf model, and in this case, it worked quite fine, and there were no real problems in deployment, other than the input of the data, which I will talk about later. And last but not least, almost last but not least, we also have a model that is doing classification of different rooms that we have extracted. And it is able to detect, is this a bedroom? Is this a balcony? Is this a toilet or closet or elevator or whatever? The way we do it is by explicitly not looking or reading any text on the image. We wanted to go away from that solution because there are different countries have different languages, and also there are different texts, and not to mention that different architects put different text on different rooms, even though they have the same classification. So sometimes somebody can put bedroom, sometimes can say this is a living room, but it also has a kitchen. It's a very messy world. So explicitly, this model only looks for some custom-made features, like how long is the polygon, or how squarish it is, how many angles does it have, and also it looks at the image itself. But explicitly, only implicitly it can learn the OCR stuff. It doesn't have the means for extracting text per se. And so we were able to achieve performance of classification quite good. But if you really think about this problem, it actually turns out that the relationship between polygons matter. So if you look at one bedroom, and if there is a small room next to the bedroom, there's high likelihood that it's a toilet or bathroom or something like that, and so on and so forth. And so if you really want to build a great classifier that doesn't look and doesn't rely on OCR or similar techniques, you really need to understand the building holistically and semantically. And so this is the project that we also have, is understanding the structure of the building using the relationship between each other. So here we are using graph neural networks, where we are architecting the building, we're extracting polygons, and we are building an adjacency graph of all the different rooms, so that we are able to say which room is connected to which room through the doors. And once we have that graph, we are able to run different operations on them. One operation, like I said, we are able to improve our classification of different rooms. But of course, that enables a lot of other different scenarios. Like now that we have this graph, we are also able to travel within the building and calculate different travel paths and so on and so forth. So that itself is a useful thing to have itself. So that was, in a nutshell, how the kinds of model that we have built, and we have relied on different techniques and different customized solutions. But even then, we have tried to unify our approach. So, for example, for object detection, we relied on detection, and for segmentation, we relied on segmentation. And that allowed us to at least unify our approaches on how we treat the data set and how we treat the deployments. Because with the startup, you have limited resources, and you need to be able to reproduce your processes as quick and as reliably as possible. So even though we are running our custom-built codes and custom models on our own infrastructure, we still try to find a common denominator. So and I think that's another lesson learned that is something worth talking about. But now that we have built this as a proof of a concept, one thing led to another, and customers flown in, and luckily it was a great success. And so then there was, of course, a big client, and the big client needed to run 100 concurrent requests, and that's it. For machine learning systems, and especially a machine learning system that has multiple models and then post-processing, that was quite a challenge. We explicitly are not doing queuing, but we're doing queuing, but we're not doing delayed processing. So we try to respond and react and treat each request as a real-time request. And so if there is a queue, there is a queue only on each node of the network. So once we had that request, we faced all of the different scaling issues. So for example, one of the issues that we had scaling up is the GPU limits. And I don't mean just in computational power, but in that sense as well. The scaling up issue is that, for example, the floor plan typically is much larger than your average ImageNet input. Sometimes it's like 15,000 by 15,000 pixels. So it's quite big. And because our models were unit-based, all of the features, all of the neural network parameters were not fitting into the memory of GPU. That was already a problem because you're, of course, limited on the cloud provider front, and there are only specific GPUs available. So, for example, we only had V100s, and that had 16 gigabyte GPUs. Actually, we were using T4 instances, so it's still only 16 gigabytes of GPU. And it just didn't fit into the memory. So our approach, of course, was to use tiling and then stitch in all of the predictions using the tiling approach. That solves the problem on a GPU level, but now that you have to do tiling, you have to run inference on every tile separately. You are running for quite longer inference times. And so for some drawings, that took longer than 60 seconds. And once you go longer than 60 seconds, you're, of course, facing the limits on SageMaker, which we still used at that point for inference. So we were deploying our models for inference on SageMaker, but because of the 60-second timeout, we could not run inference on all of the inputs that we would like to have. So that meant we had to go and take a step back and build our own infrastructure for inference, which itself means we have to also build an MLOps infrastructure, and indirectly it also led to data lineage infrastructure, and so on and so forth. So the building and training of machine learning models was only the beginning of our troubles, even though it was fun. So I'm just sharing this as a real-world experience in deploying machine learning models in the wild. So to sum up, I would like to state that some of the lessons that we learned. First and foremost, when I joined this project, I was quite shocked that that's what happens in the industry, that people just email themselves or each other PDF files, and they try to live with that. An obvious solution here would be to just measure some digitally first format and then be done with it. But, and that's probably the most important factor, is construction industry is very averse to, well, many innovative solutions. So like it's very hard to do Web3 if there is no real value in it. And construction industry is the industry that only would change if there is a real value in there. So there was no way for us to convince people just use this other format because it doesn't make sense. And also, frankly, there are bigger players in the industry who would be doing that, and they were still failing. So the lesson learned number one is just start where they are and then try to lure them in from there. Just as a small anecdote, one of the companies that we've talked to this year, they still had a CRM system that was running on DOS, and they were quite happy. So that kind of gives you the scale of change that's coming to construction. Another lesson learned, I think, is also important to point out that do build custom code, but also build it only if absolutely needed. In our experience, we try to sometimes overbuild some of the code that was then causing a lot of maintenance problems. And so that's kind of the lesson that we wanted to highlight here, is that even if you are building custom code, try to still unify it and try to, of course, rely on open source, because that's free maintenance in some sense. Also contribute back to open source, because that's rising tide lifts all boats. Maybe not very unexpected lesson, but something that keeps on coming back to me again and again, is that machine learning is far from automated. It seems like, with all the proliferation of all the no-code, low-code machine learning tools, you could be able to just stitch a few images together, call it a data set, and train your things. But it's far from that in the real world. If you really need to deploy something, maybe it's good for some proof of concept, but for a real product, it's far from automated, and who knows if it ever will be. And maybe the most trivial, but also again to reiterate that machine learning turned out to be the easy part. Like I said, after machine learning, there was also the vectorization, but even that is an easy part, because the real problem that we discovered, that even if you have this great solution that has AI first product and all of that, people still need all the other not AI parts of the product. So you still need to have all of the manual parts of the product, and you need to build it, maybe sometimes even start with it. And that's a lot of work. That's a lot of resources. And in our case, that means like very heavy focus on some front-end development, WebGL development, and going deep into these like high-level front-end libraries for geospatial information and so on and so forth. So even though we are an AI-first company, the core of our development is still not AI. The core of our development is a lot of just software development. And that's maybe what I would like to finish in, that there is a saying that AI is not IT, and I totally would agree with that, but also AI is not possible without IT. And IT, I mean software development. So let's not finish our job and not deploy and streamlit and hope that it's it. There is a lot of work that needs to be done, but the optimistic thing is that it can be done. And large industry like construction, like all of the industries that are a bit further along in innovation processes, there's still many things to do, and the world is open for possibilities. And let's build some very cool projects. Thank you so much. And if there are any questions, I guess I will be available for a Q&A. Thank you.